Good morning, everybody. On this special edition for our drone magazine, I have invited somebody that you most likely wouldn't know who is, but you most likely would have heard of what he has achieved. Good morning or good afternoon, Håvard, from the US.
Thank you very much. My name is Håvard Grip. I work for NASA JPL as the flight control lead and the chief pilot of the Ingenuity helicopter that's currently on Mars.
Can you just repeat that? It's currently on where?
At Mars, the planet Mars, that is.
Okay, the planet Mars. So we're talking about operating a helicopter at Mars today. This is going to be exciting. I know there's tons of questions that people back home there that has probably seen the pictures and the enthusiastic people behind it, which you also are a part of and leading some of the teams. But we need to get to know you also, Håvard, better before we start talking about what you actually are doing at Mars. You are originally Norwegian. Give us a little bit about your background and how you turned up at NASA.
Yeah, so my background is I'm a control engineer. And my background is, I have my education from the Norwegian University of Science and Technology. Where I worked, with control, among other things, of automotive vehicles, and then, did some work on navigation. And then, at some point I got in touch with someone at JPL, and we got talking, and it sounded interesting what they were doing, and well, I ended up working there. And shortly after I began, actually, this project, this idea to fly a helicopter on Mars came about. So I got in right at the beginning of that.
But I just need to clarify right away. Why do we want to fly a helicopter at Mars beyond that it really looks super difficult? What's the goal and what do we get by doing so?
So helicopters can do, things that ground vehicles can't do. The same reason we use, airborne vehicles on Earth for certain tasks, right? And so one of the things that's sort of most obvious is just to scout, act as a scout for a rover, or maybe even in the future for human beings on Mars. That's one, particular role for which a helicopter is very well suited. Now, we also think that future helicopters could potentially carry their own science instruments. We're looking into larger, more capable helicopters, and they could potentially get to places where we can't access with a ground vehicle.
So in terms of logistics.
Yeah, well, logistics, it's mobility, right? It's mobility. It's all about mobility. It has a different kind of mobility profile, if you will, than a ground vehicle. And we're already seeing this in our operations on Mars now. We've transitioned from our original goal, where we were just aiming to prove that you could fly a helicopter on Mars with up to 5 flights. But we've transitioned from that into a mode where we're demonstrating operability on Mars, and in fact adding value to the work that the scientists are doing in terms of performing actual scouting. At least in a couple of flights, we've actually gathered useful images that feed back to the process that the scientists are performing.
And now you're talking about something called, feeding. I know that based on the distance that we see when we look out into the space, this is a beyond visual line of operation. This is like as far out as you probably can get. Has anyone ever done anything like this before?
Certainly not flown, and powered aerial vehicle, a controlled aerial vehicle on another planetary body. That's never been done before, and that is sort of in the context of our going to Mars, was to prove that was possible. That was our number one goal, and we achieved that.
But Håvard, you need to explain to us a little bit thoroughly and what's under the hood for the helicopter. It's a long distance. I'm sure that signal is a problem. How do you control it, and how do you actually manage to do so with such a delay that there needs to be, even with the signal traveling at light of speed? Can you explain this to us?
Yeah, so it's fairly complicated in terms of how data is transferred back and forth between Earth and the helicopter. It's sent out via the Deep Space Network, which is a constellation of big antennas here on Earth, and then to an orbiter around Mars. We have, a couple of different orbiters that are used that orbit Mars, And then the orbiter transfers data to the rover, which then acts as a relay to send data to the helicopter at particular times when the helicopter is awake. And then, when we get data from the helicopter, that whole process happens in reverse. And so, of course, all of this takes time. And so it's like you say, we have to sequence commands to the helicopter that we send up. And then hours later, we then get the results of those commands back again. And we just have to be patient in the meantime.
Any trouble so far, or does things work seamlessly on operations like this?
It's worked remarkably well. It's worked really, really well. We prepared ourselves as much as we could, obviously, but you never know with a first-time activity like this how it's going to go. But it's worked remarkably well. Of course, there have been, a couple of hiccups along the way. We had an anomaly in one of our flights, flight number 6, and we also right up front had a little bit of trouble getting into the right mode for spinning the rotor at the appropriate speed. So that was, a little bit of startup trouble there. But besides those issues, things have really worked very smoothly.
I guess it's kind of hard to troubleshoot. You don't have the possibility to just be hands on it. How do you solve such things?
Yeah, so there's quite a bit of detective work, oftentimes when you're getting data, and obviously we have limits on how much data we can retrieve, how much data is even logged, that would indicate what happened if something doesn't look right. And so it's really just a lot of detective work. We've tried to instrument it the right way so that it's possible to get insight into both the performance, the control system and aerodynamics and all of the other, supporting systems. But ultimately, it can require, some head scratching, to figure things out. Now, we've become sort of used to that in some sense from working here on Earth with the helicopter over several years, testing it in a low density environment. Of course, then it's right there. You can always break open the chamber and access the helicopter, but still there's a threshold there, to doing that, and that it sets you back, enough that you get used to doing as much as you can just based on limited telemetry.
Let's just for once put everything in perspective. How far is Mars currently away from Mother Earth?
It's, I'm not sure I have the right number exactly. It's something like 300 million kilometers on that order. So it's a long distance.
How long does it take from you push the button that actually the signal is then at the drone? How long does it take?
I'm not actually, I don't have the number, exact number in my head right now, but we're talking, on the order of 10 minutes, right? That's it. Okay. It varies, but that's just the signal, traveling with the speed of light. It takes considerably longer than that from the time that the sequences are prepared here on Earth, and you go through all of the different relays and gets, and arrives at the helicopter. That takes considerably longer. So we're talking then on the order of hours for that to happen. And then,
but what about the bandwidth you have? What about the bandwidth you have available to get image back? Because I guess one thing is telling the story, but one thing is showing it. And you actually had live footage, or what seems to be a sequence with film with images put together as a film. What kind of bandwidth and possibility do you have to transfer relevant data back home?
So that, the video that was taken of the helicopter flying, right, that was taken by the rover, and so rover, has a certain amount of bandwidth that for data that it can relay back, and that exceeds what the helicopter can do, because the helicopter has to transfer from the helicopter to the rover as well. So that's a choke point there, and so the rover has higher capability, but still, when we're taking video of the helicopter flying, then we're really utilizing that as much as possible to get those nice videos.
Just give us an example. How long does it take to get an image back then, and what kind of resolution are you talking about?
So the rover can take images of many varying resolutions, and typically we do a downlink session after a sol has passed on Mars, and a lot of images arrive back. And in fact, you can see all of those images that get downlinked. They are automatically pushed out to the public on JPL's website, and so you can go there and then you can look yourself and see how many images, and you'll see it's thousands upon thousands of images there, just tremendous amount, and it's all publicly accessible.
I will see if we can actually put a link as a footer for this, so people that wants to see what it looks like can have a closer look at it. But Håvard, let's have a closer look and talk about the drone and the helicopter itself. Give us the facts about how it was built, created. What does it contain of? What does it take to actually operate in such an environment as Mars is?
Yeah, so the idea started back in 2013 in earnest, anyway, where can we fly a helicopter on Mars? And so one of the first things we had to understand then is how does a helicopter perform, especially in the low density environment on Mars? And the first thing you think about then is thrust. Can you produce enough thrust in that environment so you can lift yourself? And so that was sort of the initial focus, if you will. And what we learned as we started to try to demonstrate the fact that we could do that was that besides producing thrust, there are also other issues of how the helicopter behaves in that environment. It acts differently, or we say the flight dynamics are different, or the handling qualities, if you will. And so we had to learn about that, and that was really uncharted territory, because nobody's built a helicopter for that kind of aerodynamic environment before. And so we put a lot of resources then into modeling and simulation of that, which allowed us to understand what the key issues were. Not only so that we could control, say, an arbitrary helicopter can lift itself in Martian atmospheric conditions, but really how do we have to build it mechanically in order to make it controllable in the first place? And once we'd done that, that's when we were ready to build, a real prototype, and that we could test in low density conditions in what we call the JPL space simulator, 25-foot space simulator at JPL. And so a lot of effort was based on modeling and simulation, and then verifying those with sort of select tests in that environment. And that required a lot of creativity in terms of the test setups in such a confined space. It's not like we could just take it out for a flight. Every test is, requires a tremendous amount of preparation and in order to plan and set up and execute.
Are you able to pinpoint out some of the highlights of the major troubles that you have been able to actually solve during such a process of building it?
Yeah, so number one, perhaps, that drives everything is mass. Everything is about mass because of the low density. We have to keep the mass down. And so it's sort of like you can solve almost any problem if you have the mass to do it. But when you don't, then just a lot of things, become difficult to solve. And so taking the flight control system, for example, it's just, the computing power that you have available, the kind of sensors that you can afford to have. We have an IMU, which is called inertial measurement unit, that weighs less than a gram, for example. It's the kind of thing you find in your phone, and that's what we could afford to put on a helicopter like this, and we have to live with the performance that comes with that choice, right? So that sort of drives everything. Now, in terms of the aerodynamics themselves, there were some issues there that posed major challenges that we overcame. One of them was we discovered that if you just try to build a rotor the way that you might for Earth, it wouldn't be very easy to control. It sort of would be a little bit comparable to riding a bicycle with grocery bags hanging from your steering wheel. You get these oscillatory modes in the system. It just has to do with a lack of aerodynamic damping on Mars. And so we ended up putting requirements on the rotor that had to be extremely light and extremely stiff, the rotor blades as well as the hub and the mast. And that, of course, was also, it was a big engineering challenge to to be able to match those requirements. But in the end, we have some very good, talented people here who were able to do that.
What is the dimension of it? I read somewhere that it was about less than 2 kilos, but materials and the scale, just give us in a way the proportions of it as well, please.
Yeah, so the rotor diameter here is 1.2 meters. And so that's a pretty large rotor for a vehicle that only weighs 1.8 kilograms. And especially when you think about the fact that it spins about, the same speed that a propeller on a small airplane, about 2,500 RPM, depending on the operating point of that. So where the tips, we're around 0.6, Mach on Mars. So that sort of indicates to you what the low density does to you. It requires you to have a very large rotor and then, a very small overall weight. And that everything kind of is driven by that. Also, what it does to you is it actually makes, it worse in terms of the power requirements, the energy requirements in order to lift that limited amount of mass or, limited amount of weight because of low density. And so you have to expend a fair bit of your mass on batteries. And then, it just doesn't leave a lot of room for the other things on there.
So curiosity, batteries and sensors. What kind of sensors do you have on board? You talk about the IMU. What about the battery capacity that always is a challenge on the ground? How does that work for you, and how did you solve that actually on Mars?
So in terms of sensors first, so the sensor that we have in addition to the IMU is we have an altimeter, or it's rather a laser rangefinder, it's measuring distance to the ground. And then we have a navigation camera. So this is a black and white camera, fairly low resolution, 640 by 480, that we take images of the ground with at 30 hertz. And those are the sensors that sort of work together. They're fused in flight in order to come up with a navigation solution. And we also have an inclinometer that we use just prior to flight in order to better calibrate the IMU right before takeoff.
Yeah, because you don't have obviously a GPS on Mars.
That's right. So that's, talking about challenges again, that's, another one of those is, what is the, how do we navigate on Mars? And so we built a system that's based on visual inertial navigation. That means it tracks features, looks at features, sees where they are, and then, 1/30th of a second later, looks at, can I see those same features? Where have they gone now? And compare that to the IMU. And to do that at that speed, in a space vehicle is really, is sort of extraordinary that is possible to do. And in order to do it, we had to make some choices that were consistent with what we came there to do, which is a small technology demonstration. So it's like, well, we are going to find this nice flat area with an open space where the rover is already inspected, and that's where we can take off and land. And that means we can design, make certain simplifications in the navigation algorithm, and we don't have to detect hazards on landing. And that, of course, that's a paradigm that works really well for that technology demonstration. What we've had to do now, though, is we have the vehicle that we have, the software that we have. We designed it for this tech demo, but we're going to try to do a lot more with it. And so that's been some of the operational challenges, with what we're doing now, where we've actually been able to take that technology and operationalize it to the point where we're going from place to place, hundreds of meters at a time, without to areas that we haven't seen before, with the rover or the helicopter. And doing actual scouting. And a lot of the challenges in that is just working around those limitations of the navigation algorithm that still thinks I'm going to fly over flat ground, even though it's not actually doing that. And so we try to be as nice as we can to it in terms of how we plan the flights.
So less risks involved currently, I understand.
Less risks, you said?
Yeah. Well, I see that. It seems like you're planning low risk operations, so you can extend the duration of how long it will actually operate for you.
Well, actually, I mean, really, we've been taking larger risks. If you look at our flight profiles, when we look at the flight profiles during this phase of flights, in order to do real work and demonstrate, that the helicopter can be as useful as we think it can be, we've had to take risks, and that involved, for example, we took the helicopter on a flight more than 600 meters across very variable terrain, low texture part of it, and large variations in the height of the terrain, something that it really was not designed to do. But we tried to play as nice as we could with it to reduce that risk. So we fly more slowly over certain regions where we know is particularly challenging for the navigation algorithm. We found in orbital imagery a large area that's mostly sandy, so that it would be have larger margin for error on landing and so on. But working like that with the helicopter and sort of knowing its limitations, we found that we were able to do fairly advanced things despite those limitations.
How many minutes of flight do you have, and what's the duration that you see that you can obtain with the batteries that you have today?
So we've flown up to about 170 seconds, and that's from takeoff to landing. And then in addition to that, there's some amount of time on the ground where the rotor is spinning both up and down and at full speed. And of course, you also use battery when you're idling as well, or the rotor spinning at all. So that gives you some sense of the duration. So, it's short bursts, but still quite a lot more than what we envisioned. The goal was have 90 seconds of flight time. And so we've come, fairly close to doubling that. And that makes a huge, it makes all the difference in the world. That combined with having been able to work up a ground speed that's also much larger than what we originally baseline. We can do way more than we thought was possible.
What kind of speed can you achieve on that helicopter?
So what what the physical limitations are is one thing, and then there's the sort of constraints that we put on ourselves in order to try to keep it safe. And there are a couple of things there that come into play. One is just airspeed. In the aerodynamics, in terms of aerodynamics, of course, it comes down to airspeed, and we don't know what the winds are like, and we don't control to airspeed. We don't measure it. We control ground speed, and so we always have to set a ground speed that, with whatever additive wind that we think we're going to see, that we're still safe. And then another thing that comes into play is back to the navigation again, because we're tracking these features that are, sort of gradually disappearing below us. We have to make sure that, we see the same features for enough time, that they don't move off too fast. And so that's another limitation. And so what we've been able to do so far is we've been going at 5 meters per second ground speed. I believe we can probably go faster than that, but that's as fast as we've gone to this point, and we'll see if at some point we feel that we'd like to push that further.
What about the battery? How long does it take to charge, and what kind of battery will actually last on the temperatures that you have on Mars, and how does that affect performance for you?
So these are commercial batteries, and I don't have the parts number, memorized, but it's actually available. If you look up, some of our papers, you can find, exactly which batteries we are using. But they're commercial, off-the-shelf batteries, as is a lot of the stuff that we are using. When we talk about why is this possible to do at this point, a lot of it comes down to relatively recent developments in commercial technology, and batteries is one of those things. Solar panels, the avionics is based on commercial off-the-shelf computing platforms, the sensors as well. It's like cell phone and drone technology, and the fact that those things are now available and are as lightweight as they are, that's enabling for being able to do this kind of thing.
Håvard, you are in a way with your team pushing limits that's beyond, I think, the imaginary capacity for many of us, because you're putting so many difficult challenges together in one project. What was your feeling when you actually, for the first time, realized that this was possible and actually did do flights at Mars?
It's been very sort of gradual in a way, right? You kind of, certain elements of it almost seem like, it's too challenging, or, is it even possible, until you worked enough at it and you found the solutions. And sort of that's been a gradual process for many years now. But even when we got to the point of, hey, we're going to actually fly this thing, it just takes it to a whole new level. It's all going to work right now on Mars, in this environment that it's never seen before. It's now, sitting out there in the breeze, so to speak, with the environment tugging at it, and it all has to work. And so it was a little bit of almost disbelief when we then, got it in. So, it really did, all come together perfectly, on that first flight attempt.
But Håvard, I mean, a little bit of a bold question for you, but I mean, since you managed to actually operate a drone and a helicopter at Mars, that seems to be an incredible achievement for many aspects. Can you help us solve some of the problems on ground and Mother Earth, like, for instance, drone logistics? I mean, we're dealing with challenges like just having a drone be flying blood samples or emergency equipment from A to B on ground. Can you help us solve that, please?
I think, it's quite possible that there are elements that can transfer, right? Things that we've learned and part of the research that we've done that could be utilized for Earth applications. Frankly, I don't, necessarily know enough about exactly, what those needs are and where, our research might fit into that. I've been very sort of tunnel vision focused on the Mars application for all these years. But I think, could there be things like that? Sure. I hope that there are things that we've done that could prove useful in other areas as well.
So where do you see actually this leads? I mean, you've done something which is so extraordinary. What will be the next thing? Is that moving? Do you see any transition from going from where you're now to moving people on Mars with a helicopter or drone, from moving goods? So what kind of transition and pace do you see this will work in? I mean, it took you some years to get where you now are.
Yeah, so I think, when you're looking at future helicopters, it's still limited, payload capacity, in the sense that, if you were to try to carry a human being on a helicopter on Mars, you would be talking about a rotor size that's probably beyond, what's manageable. That's just the limitations of that, of the density of the atmosphere there. What we're talking about is more on the order of 10, 15 kilogram vehicle. With a payload capacity on order of a few kilograms, and so what we hope we could fit into that is certain types of science instruments, and so then it's sort of up to scientists to use their imagination about how they could best utilize a platform that has the kind of mobility that the helicopter has. Can't carry as much weight as a rover, but it has a different kind of mobility. So how do you best leverage that? And I think that's a process that's ongoing, with people thinking about how that kind of technology can be best utilized.
Håvard, last question for you. Why Mars?
Well, NASA has had a long-term focus on Mars, right? It's a planet of great interest in terms of the geological history, and could there potentially have been some kind of life forms there in the past. And so that's the context for all of this interest in that planet, and of course we had this mission that was going there, Mars 2020, the rover, that's been in the works for a long time, and so it was a natural thing with that mission being planned on this time frame to look into, well, how about adding a helicopter to that. And it happens to have an atmosphere, barely, but it has enough of an atmosphere that it is actually possible to fly there.
Sounds good. Håvard, I think I say for a lot of us, we really look forward to hearing more about the new exciting project, but also the results and especially also images that you are working on. And we hope to see you soon in Norway to share the rest of the story of what happens behind the scenes at NASA. Thank you so much for joining us today.
Thank you very much.
Safe to Fly, en app for alle brukere av droner. Tjenesten alltid oppdatert og enkel å bruke slik at du finner all informasjon du trenger på ett sted. Fly sikkert. Alltid.